So the first type of forces that we're going to examine here are balanced forces. We can see this crazy balancing act in this image. How are these things able to stay balanced? Well, this guy right here is applying a force down this way, while this shovel right here is applying a force over here. If these forces are equal, then we get balance right there. Now, doing a system like this would require us to apply some torques, way too advanced for us right now. But the basic idea is there. If we have a force going to the right, and I want to balance that force, I could have a force going to the left. And if I have these two forces, force 1 and force 2, being equal to each other, there'll be no net motion. And so we can have things under a force that aren't moving. For example, you sitting, watching this video, you're probably not falling, but you have gravity pulling you downwards. Force of gravity is pulling you down. What's holding you up? Probably the chair you're sitting on or the floor you're standing on. That is what we call a force normal. It's a normalizing force that the surface you're sitting on is pushing back against you to keep you from crashing through it. If that force normal wasn't big enough, you would break through the chair. This is what happens if you're standing on ice that's too thin. The force it can't apply a force normal big enough to support your weight, and you crash through. So these are pretty simple to examine. If I just say the force of gravity is 40, what does the force normal have to be? Negative 40. Easy. But what about forces that are in different directions? What if I have a system? Let's draw a little box here. Let's say that box has a few forces acting on it. Let's give it force 1 is going at 45 degrees and has a magnitude of, let's say, 10. And then it's got another force. Let's say this force is going down, and this angle right here, let's say this is 15 degrees. And this force is 15. What would be a third balancing force? Would it be straight out this way? Would it be straight to the back at 0 degrees? Or would it be 15, 10, somewhere in between? What would that force need to be? Well, there is a way that we can figure this out. Because what we're really saying when we balance forces is that if I take my F1 plus my F2 plus my F3, and all three of these would be vectors. So we give it this little sign to say, hey, this is a vector. We're not just adding these numbers. They also have a direction that we would add together. But if I have a balanced force, I'm saying these three together will come to 0. Now, these being vectors implies that they have an x and a y component. So I could really say f1x plus f2x plus f3x, and those would be straight numbers. Those would be 0. And I could say that f1y plus f2y plus f3y would equal 0. So if I make that equation, I should be able to solve for f3, shouldn't I? If I can split these up into their individual components, I should be able to solve this. Let's try it. Let's create ourselves a little table to help us keep everything nice and straight. All right, we've got a table set up here. I've called the actual number here the magnitude. For our F1, we're going to make this our blue. So this will be F1. F1 will be blue. Our magnitude is 15, and our direction is 15 degrees. But is it actually 15 degrees? If I just apply 15 degrees, what's the difference between that 15 degrees? How do I know what this should be? So let's take a pause here and let's define some directions. Whenever we're looking at 3 dimensions, let's get my zoom back to normal. Whenever we're looking at 3 dimensions here, we use something called the vector plane. This is going to be very similar to something you've already seen. If you've seen graphs with 4 quadrants before, we have the furthest right being positive, up being positive, down being negative, further the left being negative as well. If I want to talk about angles here, I can think of this as one big circle, and that can allow me to define my vectors in any direction. So First, my positive here, this positive to the right, we call that 0 degrees. You'll also hear this called east. My up direction is 90 degrees, and you'll hear this called north. These align with the cardinal directions. And then my first negative, my furthest left, would be 180 degrees. We call it west. And then south is 270. And 0 degrees could also be 360 degrees. Now, if you were to take any number and you said, hey, this is 90 at 270 degrees. Terrible at writing. Then if you took the cosine of 270 degrees, cosine of 270, you would find that to be 0, because the cosine would be this angle right here. And that's going to be 0. There's nothing going that way. If it's going all at 270, cosine would have to be 0. The sine of 270, you would find that to be negative 1. So if we can apply our directions in this format, it is extremely helpful to us because it will take care of our positives and negatives right off the bat. And we'll be able to communicate objectively which direction we're moving. This is something that pilots, aerotech engineers have to be cognizant of, because if they say, hey, put your bearing at 15 degrees. 15 degrees from what? If you say 15 degrees west of north, that means 15 degrees west from north. That would be 90 plus 15. That would be 105 degrees. We know exactly what direction that should be. So this is a pretty important way of categorizing that information, and we're going to use that when we categorize these types of forces. So first thing, I've got 15 degrees. This is going to be 15 degrees from 0. This is going to be 15 degrees from 360. So this 15 is from east. So this would be south of east, 15 degrees south of east. So I would take 360 minus 15. That would give me 345. Let's put that in blue. All right, and then F2. F2 is at 45 degrees. So this is going to be 10 at 45 degrees. That's simple. That's going to be from 0 because it's in the positive plane. Okay? So I can see that. It's in the northeast plane. Everything's positive. I can see this is in my southeast. Down is negative. Right is positive. Great. So now I want to break these into their component vectors. And I'm going to do that using SOHCAHTOA. And so to find my x for F1, I'm going to take F1 times the cosine, because cosine is going to be the adjacent angle. So the cosine of 3, 4, 5. If I put that into my calculator, I get 14.5 in x, and now I can take F1 times the sine of 345. And that should give me my y. And just like we established, that gives me negative 3.9. That is a negative. That's what we expected. Now let's do the same thing with F2. It's my red, right? Let's put this in red. So F2 cosine of 45, F2 sine of 45. So 10 times the cosine of 45 is going to give me 7.07. Then 10 times the sine of 45, you may already know this, it is also going to be 7.07. Whenever we have 45 degrees, our x will equal our y. So now what do we do? Well, we've established that these equations must hold true for this thing to be balanced. So I'm going to do that. I'm going to take these x numbers, I'm going to plug them into my x equation. I'm going to take my y numbers, plug them into my y equation. Let's do that below. I'm going to do purple for x, and so my F1 and x is going to be 14.5 plus 707 plus F3 equals 0. So I'm just going to subtract both of these from both sides, and I should get my x for F3. And that's going to give me 21 point, I'm going to round this to 6, 21.6. All right, and then we need the y. And the y is going to work the same way. I'm going to have, and I'm going to do this one in green, my y. So this is my x, this is my y, and that's going to be negative 3.9 plus 7.07 plus f3 equals 0. So I'm going to add 3.9 to both sides, and I'm going to subtract 7.07 for both sides. And when I do that, I should get negative 3.2. We'll round it 3.2. So now I have the x and y for f3. Now, what can I do with that? Well, this is going to give me a triangle. My y is going to be down, right? It's going to be down. And my x is going to be positive. It's going to be in this direction. Should it be positive? Oh, that should be negative. My bad. And so my resultant vector will be the addition of those two. And so it'll be something like that. And so I'll get an angle on it, and I'll get some numbers to this. Let's redraw this in a slightly different way. If I want to draw this so that I can easily make that line, I want to make that line and see the triangle in it. Then I can just make a square out of my two vectors. And so now I'm going to have this angle. I want this angle from 0. This is my 0 degrees. I want to know what this theta is. That's what I'm going to put right here. That's going to take some figuring though. So in order to figure out that angle, I need to rely on my trigonometry functions again. And here I'm going to use tangent. So tan theta will equal the opposite over the adjacent, which the opposite here, the opposite of this angle, would be my y. So y. The adjacent would be my x. So x. So tan theta equals y over x. So tan negative 1 of y over x will give me theta. So that's how I can solve these functions. So now I need to put y and x in here. So tan negative 1, taking negative 3.2 divided by negative 21.6, and I get 8.42. Wait a minute, shouldn't that be bigger? Shouldn't it? This is 8.42. What number did I really get here? Well, I got this angle between this purple line and this white line. So how do I get to this line? Well, if I want to keep things objective, whenever I use tangent, if I use any of the inverse sine, cosine, or tangent functions, they're never going to give me a number above 90 because they're going to give me everything in terms of a right triangle, not in terms of this vector graph. I can input a larger angle, but it's never going to output that larger angle. It's always going to give me something between 0 and 90. It's always going to give me that angle relative to the x-axis though. So when I say I've got 8.42 degrees and it's positive, I see that my x is negative, so that means I'm going to be over here. I'm going to be over in this direction. My x is positive, or my x is negative, and my angle is positive. So I start at 180 degrees, and I'm going to go from 180 degrees. So I've got 180 plus that number that I just got. 180 plus 8.4 would be 188.4. If this number was negative, I would take the x-axis that I'm at. If I'm all positive, I'm going to be at 0 degrees. If I'm all negative, I'm going to be at 180. If it's negative, I'm going to subtract that value. If it's positive, I'm going to add it. So if I was in this quadrant, I would get a positive value. I could get a positive 15 and I would add it to 0. If I was in this quadrant, I would get a negative 15 and I would subtract that from 360. So that's how we can figure that out. It's going to take some finagling, but we can do it. Now we need the magnitude. And that is actually a lot simpler than using the tan negative 1. That's going to be a squared plus b squared equals c squared, the Pythagorean theorem. So we just input these values. we've got negative 21.6 squared plus negative 3.2 squared. Take the square root of that. Now, if you just plug this into your calculator like this, it might give you an invalid. And that's because your calculator sees that negative, sees this square root, and says you can't square root a negative number. That doesn't exist. So you might need to make sure you put parentheses around this, or since squaring it is going to make a positive number, we just don't have to worry about those negatives. And when I do that, I get a 21.8. So I'm going to be 21.8 at an angle of 188.4 degrees. Fantastic.